Hello everyone, and welcome back to this series on intermediate statistics, and today we're going to be continuing our exploration on how to estimate parameters with statistics, in particular how to find meaningful or good choices of statistics to estimate parameters of populations with. So let's assume that we have a sequence of random variables xk where k ranges from 1 to m, and let's assume that that sequence is a sequence of independent and identically distributed random variables, and let's assume they're all coming from the same exact population where this random variable is going to be represented by x. Let's also assume that we're going to be calculating a statistics called theta hat from that particular sequence, and let's assume that that sequence is xk. So for example, we can take all the x values, add them up, divided by how many you get, and that would be a statistic. So x bar would be an example of a theta hat. So if theta, without the hat, is a parameter of the population, then we say if and only if the expectation of that random variable theta hat is equal to that parameter theta, then we say that theta hat is an unbiased estimator of that parameter theta. So to sort of guide us on our little exploration of how to find a suitable theta hat for parameter theta, I want to use an example to or a particular distribution to guide us. So for our example, let's assume that x is exponential. And let's assume it's exponential with parameter theta, where its probability density is fxx is equal to lambda e to the minus lambda x for x greater than or equal to 0 and 0 otherwise. All right, so that's our exponential density function. But notice that there is a parameter inside of this distribution. So a natural question to ask is, what if we do not know theta? So what if we don't know theta? Okay, so we can always grab values from this population even though we do not know what that population looks like, right? So how do we approximate theta, right? And let's of course restate our primary question that we seek to answer: how to find a suitable theta hat for particular parameter lambda. So one mechanism that is used to find estimates is what we call maximum likelihood estimators. So let's just introduce a couple mechanisms that we're going to need in order to define what those are. So let's define a function L of theta of sequence xk, and this is going to be defined to be equal to the product from k is equal to 1 to n of the probability density functions for each of those xk's evaluated at little xk. And let's assume that each of these are dependent on our parameter theta. Right? So xk is a sequence of independent, identically distributed random variables, but keep in mind just because they are independent, right? So let's just make a very important note. So identically distributed and independent does not imply that each of them will take the same value. So you cannot just replace xk with x, 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 and x n times, right? Because they could take different values even though they come from the same exact population. So L is a function of our parameter theta that we seek to estimate, and xk is our sequence coming from our identically distributed sequence of random variables, right? So for our particular example, what is that going to look like? So since it's a exponential distribution, that's going to be equal to lambda e to the minus lambda xk. So we can actually multiply these things quite well, because keep in mind, what is that going to be equal to? So it's lambda e to the minus lambda x1 times lambda e to the minus lambda x2 all the way down to lambda e to the minus lambda xm. Notice that we're going to have n lambdas in the leading coefficient, and since we have exponentials all with the same base, we can add those exponents, factor out that minus lambda, and then we're going to have x1 plus x2 plus x3 all the way down to xn inside of that exponent. So for the exponential distribution, the likelihood function, L lambda of xk, will be equal to lambda to the power of m e to the minus lambda times the sum from k is equal to 1 to m of xk. Right? We have this function here, which again we call the likelihood function. The likelihood function. So one of the very first things you want to do when you want to try to find a maximum likelihood estimator is to find this likelihood function. Now a couple little observations. The center of L, this likelihood function, because it's a function, so it should have a middle or an expected value or a median, and or perhaps the value that maximizes L are good choices for the lambda value that would estimate lambda parameter. So this theta hat is called the MLE of theta, right? So theta hat is the value that maximizes the likelihood function, right? So keep in mind what we mean by maximize. So we find our likelihood function, we differentiate it, set it equal to 0, solve for theta, but that theta is a particular theta for which we call theta hat, right? So theta hat is called the MLE of theta if it satisfies two properties. One, it maximizes the value of the likelihood function for that parameter, and two, it is unique, right? That is, it has a unique maximum, right? So here we have this theta hat, we call it an MLE if it maximizes the likelihood function. Right, so therefore, what does that mean? So therefore, theta hat is the MLE if the partial derivative with respect to theta of the likelihood function for theta under that sequence xk evaluated at theta is equal to theta hat is equal to 0. Now, there are a couple complications with this likelihood function because keep in mind we're going to take the derivative with respect to our parameter theta. We have a likelihood function generated from a product of a bunch of probability densities. So if you do not know the general product rule, because we have function times function times function times function times another function, generally speaking, that can get really messy to work with. So just a couple observations. One, L theta usually has exponents since it is due to the product of our density functions. And secondly, the natural log of x is strictly monotonic increasing. And what does that mean? So if we look at the derivative or the graph of the natural log function, it's always increasing. So if you want to take the derivative, you should be able to verify that it's always positive. So under these three things, because we know natural logs actually turn products into sums, and the natural log is strictly monotonic, and we want to maximize the likelihood function. So bringing these things together, L theta xk is maximized if and only if the natural log of the likelihood function, theta xk, is maximized. Note that since we're taking the natural log, we cannot feed it negative numbers or 0. So one important thing you should be able to verify is that the likelihood function is always positive. It's never 0. It's never negative. Because if it is, this new function, the log of the likelihood function, won't exist. So for our particular example, what is the log of the likelihood function for an exponential sequence? Well, that's just going to be equal to the natural log of lambda to the power of m times e to the minus lambda times the sum of our xk, where k ranges from 1 to m. And then we can decompose the natural log of a times b as the natural log of a plus the natural log of b. So that's going to be equal to the natural log of lambda to the power of m plus the natural log of e to the minus lambda sum of xk. Notice that this exponent can come down by properties of logs, and the natural log and e are inverses of one another, so they eliminate, just dropping that exponent down to the ground. So what we have here is this new function, L lambda xk, which is defined to be equal to the natural log of L lambda xk, is going to be equal to n natural log of lambda minus lambda times the sum from k is equal to m of xk. Right? So we have this particular function, and we have this particular definition. So this is called the log likelihood function for parameter lambda under sequence xk. Right? So our likelihood function is maximized if and only if the log likelihood function is maximized as well. So now we have the log likelihood function for an exponential distribution. So let's see if we can maximize the log likelihood. So if we take the partial derivative of our log likelihood function with respect to our parameter lambda, that's going to give us n times 1 over lambda, which is going to be n over lambda. And then keep in mind the sum of our xk is just a number as far as lambda is concerned. So that's just going to be equal to number times our lambda, which is just the number by the power rule. And that's going to be the partial derivative with respect to lambda. Now we're going to set this expression equal to 0. And then we're going to be solving for our lambda, which we're going to call lambda hat. So we're going to have n divided by lambda hat minus the sum from k is equal to 1 to m of xk will be equal to 0. Add the sum to the right-hand side, and then reciprocate your expression, and then multiply by m. That's going to give us what? So it's going to give us lambda hat will be equal to, actually let's do 1 over lambda hat will be equal to the sum of xk divided by m, which we can call x bar, because that's just the sum of the values divided by how many you got. So 1 over lambda hat equals x bar, which means that lambda hat will be equal to 1 over the average. Right? So what does that mean? So that means that 1 over x bar is the maximum likelihood estimator of lambda. Right? Because lambda hat is the maximum likelihood estimator of lambda. Therefore, 1 over x bar is the maximum likelihood estimate of lambda as well. Now, does this make sense? Well, it should, because if you remember something special about the exponential distribution, the expected value of xk is equal to 1 over lambda, right? So this is an approximation for 1 over mu x, which is equal to lambda. So we clearly see that lambda hat is approximating lambda as it should. Isn't that neat? So we have that the average of our observations still is a good estimate for that object. Now notice that we didn't really show that it was indeed a maximum likelihood estimator. We just showed that it is an optimal value for the likelihood and log likelihood function. We didn't really show that it was a maximum. Right? And moreover, we didn't prove that it was unique. Now, we do only have one extreme point, so since we only have one extreme point, the only thing we really need to do is just verify that it is indeed a maximum. So if we take the second derivative of our log likelihood function with respect to lambda, so we're going to have partial squared L partial lambda squared, that's going to be equal to the partial derivative with respect to lambda of n over lambda minus the sum from k is equal to 1 to n of xk, and that's going to be equal to minus n over lambda squared. Keep in mind n is positive, lambda squared is always positive, and non-zero. So this is always going to be less than 0 for all m. Right? So that means the second derivative is always negative, which means the function L is concave down. That means that lambda hat equals 1 over x bar is indeed the maximum likelihood estimator of lambda. Right? And that completes the proof of that very useful theorem. Now let's consider our second example, and this is a very important one as well, but it also demonstrates another very useful thing for maximum likelihood estimation theory. Suppose that x is a normal random variable with mean, mu, and variance, sigma squared. How many parameters do you see now? You should see 2 parameters. So is it possible that we can actually estimate both of these parameters simultaneously? The answer is yes. So firstly, what is the probability density function for a normal random variable? So you may remember that's going to be fxx is equal to 1 over sigma square root of 2 pi times e to the minus 1/2 times the z-score, x minus mu over sigma, the quantity squared. And keep in mind x can be any real number. So that's going to be our probability density. So how are we going to find our maximum likelihood estimates for mu and sigma squared? First, we need to find the likelihood function. So what is the likelihood function? So the likelihood function for both parameters, mu and sigma, under some sequence xk, is going to be equal to, again, the product of your associated probability densities for each variable x1 through xm. So that's going to be equal to 1 over, so this coefficient is going to be multiplied by itself n times, so that's going to give us sigma to the power of n, and then 2 pi to the power of n divided by 2, and then we're going to have e to the minus 1/2, and then we're going to have our sum from k is equal to 1 to n of xk minus mu over sigma, the quantity squared. So that is going to be the likelihood function for a sequence of normal random variables. Once we have our likelihood function, then we can find the log likelihood function. So that's going to be equal to little l of mu sigma, and we can write it as sigma squared if we want to, of xk will be equal to, so we're going to be taking the log of this expression. So we're going to be taking the log of this, and then the log of that, since there's our multiplication right there. Since this is the bottom to the power of -1, technically speaking, then we can write this as negative natural log of sigma n 2 pi n over 2, and then we're going to have a minus 1/2, so that's the natural log of e cancels, of the sum from k is equal to 1 to n of xk minus mu over sigma squared. Right? Since this is also a product of 2 numbers, one has just a number in it, the other has sigma in it, and sigma is one of our targets. It might be beneficial to just break that up as well. So I'm going to write our final form for our log likelihood function. So log likelihood for mu and sigma squared for xk will be equal to, let's write it as minus n, natural log of sigma, minus n over 2, natural log of 2 pi, minus 1/2 times the sum from k is equal to 1 to n of xk minus mu over sigma, the quantity squared. So there's our beautiful log likelihood function for normal sequences. Now we want to optimize it. So we want to optimize it with respect to mu, and we also want to optimize it with respect to sigma squared, moreover optimize it with respect to sigma. So we're going to be doing 2 partial derivatives here. So let's just break this up. So number 1. So let's take the partial derivative of L with respect to, let's go mu first. So notice that the first term does not have mu in it. The second term doesn't have mu in it either. So the only thing I really care about is this last term, so I need to use a chain rule. And keep in mind derivatives are linear operators, so I can distribute it inside of the sum if I want to. So that's going to be equal to minus 1 times the sum from k is equal to 1 to n, since the 2 and the 1/2 cancel. And then we're going to be left with xk minus mu, all over sigma, the 2 is no longer there, and times the derivative of the interior function. Keep in mind xk over sigma is a constant as far as we are concerned, so we're just interested in the minus mu over sigma term inside of our brackets. So that's going to be equal to minus 1 over sigma, and that would be the non-simplified version of our derivative. Now let's see if we can clean this up just a little bit, because we do have a negative number in the front, and this negative 1 over sigma that doesn't have k in it, so we can technically factor that out. So that's going to give us a very nice expression. So partial L, partial mu will be equal to 1 over, and oh, notice we have a sigma and a sigma, so we actually have 2 sigmas there, technically sigma squared. So this is going to be equal to sigma squared times the, so what are we left with? So we're going to left with the sum from k is equal to m. So we have our xk term. And also we're adding mu n times, so we can write that as minus m mu after we take the summation. And we can, what can we do here? What can we do here? So we can multiply that by m, because then that turns into an x bar, and this probably is the nicest way you could write it. At least I think so. Maybe I'm wrong. So we're left with 1 over sigma squared times, let's write it as n x bar. Let's actually factor out that n, just for fun. So n times x bar minus mu. Yeah, this is a nice representation. So partial L partial mu is equal to this. Now, before we set it equal to 0 and solve for mu, I first want to get the partial derivative with respect to sigma also, so that we can solve them simultaneously. So partial L partial sigma, and you might want to pause this video to start to see if you can get this expression too. This is going to be equal to minus n over sigma minus 1/2 of the sum from k is equal to 1 to n of xk minus mu over sigma, the quantity squared. The sigma becomes sigma squared. So we have to take the partial derivative with respect to sigma. Sigma, that's not a sigma, that looks like a theta. Sigma of 1 over sigma squared, right? So once we do that, this is going to be equal to what? So keep in mind, that's sigma to the power of minus 2. Minus 2 comes down, power becomes 3 on the bottom. So this is going to be equal to minus n over sigma plus 1 over, the 2 cancels with the 1/2. Then we're going to be left with sigma cubed times the sum from k is equal to 1 to n of xk minus mu, the quantity squared. That's partial L partial sigma. Right? So we have partial L partial mu, partial L partial sigma. Now we're going to set each of these equal to 0 and then solve simultaneously. So what's that going to give us? So let's just summarize. So we have 1 over the first statement. So now we're going to replace sigma with sigma hat, mu with mu hat. Sigma with sigma hat, sigma with sigma hat, mu with mu hat, and solve for mu hat, sigma hat correspondingly. So we're going to have 1 over sigma hat squared times n x bar minus mu hat is equal to 0. And then let's write the second equation 2. We're going to have 1 over sigma hat cubed times the sum from k is equal to 1 to n of xk minus mu hat squared. And that's going to be equal to this constant on the right-hand side. So that's going to be equal to n all over sigma hat. So solving this first equation, this is actually pretty easy. Multiply both sides by sigma hat squared to divide both sides by n, since n is non-zero. And then we're going to be left with mu hat is equal to x bar. Are you surprised? So x bar, the sample mean for a normal distributed sequence, is a maximum likelihood estimator, possibly. We didn't verify that it is indeed a maximum for mu. Right? So that's actually pretty nice. So substituting that into this expression, what do we get? So we're going to have 1 over sigma hat, the quantity squared, times the sum from k is equal to n of xk minus, so mu hat is now x bar, so I'm just going to be replacing that with x bar now. And that's going to be equal to n all over sigma hat. Multiply both sides by sigma hat squared, and that's going to give us the sum from k is equal to 1 to n of xk minus x bar, the quantity squared, will be equal to n times sigma hat. Sigma hat squared, sigma hat squared. Okay, the next thing I want to do is, let's divide both sides by n, because we're trying to solve for sigma hat or sigma hat squared. So that's going to give us sigma hat squared will be equal to this thing divided by m. So they cancel. And what I also want to do is multiply top and bottom by m minus 1. This is going to give us something very special. So this is going to be m minus 1 all over n times the sum of xk minus x bar, the quantity squared, from k is equal to 1 to n of m minus 1. And this object right here inside of this brackets, that's obviously the sample variance. So we have that sigma hat squared is equal to 1 minus 1 over m times the sample variance. Right? So we have that, and we have mu hat is equal to x bar. Right? I'd leave it for you to verify that these are indeed the maximum likelihood estimates for those sequences of normal random variables. Right? So once you verify that those are indeed the maximums, then we can conclude. So the maximum likelihood estimator, the MLE for short, so the maximum likelihood estimator for mu is x bar. And if you remember, there's another special property about this. Also remember that the expectation of x bar is equal to mu as well, right? The same x bar. So this means that the maximum likelihood estimator is an unbiased estimator too. Estimator of mu. So the maximum likelihood estimate is also unbiased. Now let's take a look at sigma squared. So the maximum likelihood estimate for sigma squared is 1 minus 1 over n of s squared. And if you take the expected value, then we're going to have the expectation of this estimate, so sigma hat squared, that's going to be equal to 1 minus 1 over m times the expectation of s squared. But remember that s squared is an unbiased estimator of sigma squared, so it's going to be equal to 1 minus 1 over n times sigma x squared, which is not equal to sigma squared. So therefore it's not unbiased. That means it's a biased estimate of sigma squared. But there is one piece of light in this particular object, because as n goes to infinity, this expectation, the expectation of theta hat squared, converges to sigma squared, converges to sigma x squared, right? So this means what? So that means the maximum likelihood estimate of sigma squared for a normal sequence is biased for sigma squared, but it is asymptotically unbiased for sigma squared, right? And keep in mind, who am I talking about? I'm talking about this particular object here. So that's the MLE of sigma squared. It's biased, but it is asymptotically unbiased, since sigma hat squared, the expectation of it converges to the sigma squared. But keep in mind, that's only true if n is arbitrarily large, which sometimes is impossible for practical samples. All right? So here we have one way of estimating or constructing estimates for parameters using maximum likelihood estimation. Now, is it the only way that you can construct estimates for parameters? The answer is obviously no, but MLEs is definitely one of the more famous ones to at least start on. And also we've just sort of discussed how unbiasedness can play a role for maximum likelihood estimates. Sometimes they're unbiased, sometimes they're not, and then also sometimes they're at least asymptotically unbiased. Hope you enjoyed this video, and I'll see you in the next one. Take care.